Hello everyone, it's your physics teacher Dr. Kumar, and today we are going to discuss about the part 2 of electricity and magnetism. So let's begin. So in this short video we'll be discussing about mainly the capacitance and its properties and applications. So a capacitor, sometimes called a condenser, is a device that can store electrical energy and usually consists of two conducting objects, usually plates or sheets of metals, placed near each other but not touching. Capacitors are widely used in electronic circuits. They store charge for later use, as in camera flash and as energy backup in computers. So this is a capacitor. These are two plates, metal plates, which are situated very close to each other, and in between these metal plates it might be air or any dielectric material can be placed in between these two plates, and when these metallic plates or when this capacitor is connected to the positive and negative terminals of the battery, so what will happen? So as we know that all metals contains free electrons, and these free electrons are responsible for the flow of electrical current. So when one of the plate is connected to the positive terminal of the battery, so the electrons which actually resides on these plates, so it will accelerate towards the positive terminal of the battery. Similarly, the plates which is connected to the negative terminals of the battery, the electrons from the battery will move towards the plate. So due to the flow of electrons from this plate, so this plate will be positively charged. That means this plate contains less number of electrons, whereas this plate where the electron flows from the battery to the plate, so this plate contains more electrons, and this plate becomes negatively charged. So this is the way we can charge a capacitor with the help of a battery. So these are the photograph of some capacitors which are used in different circuits or different electronic circuits. So what is the capacitance of a capacitor? So the capacitance of a capacitor can be defined as the charge required or the net charge required to raise the potential by 1 unit. So if we consider capacitance of a capacitor as C, so C will be equal to the Q divided by V, where V is the potential difference between the two plates. So these are the representations of capacitors in a circuit. So the SI units of capacitance is farad, and 1 farad is equal to 1 coulomb per volt, and since farad is a very large unit, so practically most of the times the capacitance of a capacitor is represented by microfarad or in picofarad, which is 10 to the power minus 12 farad. Now let's see what is the capacitance of a parallel plate capacitor. So in a parallel plate capacitor, the two plates are situated parallelly to each other, and suppose D is the distance between these two plates having area A. So in this case, the capacitance of a capacitor is represented as C is equal to epsilon into A divided by T, where epsilon is the permittivity of the medium in between these two plates. Therefore, the capacitance of a parallel plate capacitor depends upon the area, then the distance between the two plates, and the permittivity of the medium in between these two plates. So you can see that the capacitance is directly proportional to the area of the plate. So if we increase the surface area of these plates, then the capacitance increases. That means if you increase the surface area of the plates, these plates can hold more charged particles, and that means electrons, and so the net potential difference will also increases. And you can see the capacitance is inversely proportional to the inversely proportional to the distance between these two plates. So if we increase the distance between these two plates, then the capacitance of this capacitor also decreases drastically. So to have a high value of capacitance, so one should require to place these two plates very close to each other. And another thing is that this capacitance is directly proportional to the permittivity. So one thing you should remember that when you place these two plates very close to each other, and if you apply a high voltage between these, or high potential difference between these two plates, then there is a possibility of discharge. That means there is a possibility of current flow through the air medium, through the air medium. And therefore in order to reduce the possibility of discharge between the air, so sometimes dielectric materials are placed in between these two plates. So dielectric materials have very high breakdown voltage, and so by placing a dielectric material, you can bring these two plates closer to each other. So this is the basic construction of a parallel plate capacitor. These are the two plates, and this is the dielectric medium. And with the help of dielectric medium, you can bring these two plates very close to each other. So most of the electronic circuits, we need to connect 2 or 3 capacitors in order to get a desired capacitance. And therefore there are 2 ways to connect these capacitors, that is parallel combinations of capacitors and series combinations of capacitors. So let's talk about the parallel combinations of capacitors. So let us consider this circuit. So C1, C2 are 2 capacitors, and these 2 capacitors are connected parallelly with a battery whose potential difference is or whose voltage is V. And why these 2 capacitors are called to be in parallel combinations? Because the potential difference these 2 capacitors experience is equivalent. And let us consider that Q1 and Q2 are the charges of C1 capacitor and C2 capacitors respectively. So the total charges that leaves the battery will be equal to, that is Q will be equal to Q1 plus Q2 equal to this. Okay. And let us consider that the equivalent circuit of this circuit is this one. So the equivalent capacitance, suppose it is represented by C equivalent. So the C equivalent can be represented by equations 2, and therefore putting equations 2 in equations 1, we can get C equivalent equal to C1 plus C2. Therefore the net effect of connecting capacitors in parallel is thus increase the capacitance. So if there are n numbers of capacitors connected parallelly to each other, then the equivalent capacitance of the capacitors will be equal to this one. Okay. On the other hand, in series combinations of capacitors, the capacitors are joined end to end to a battery. So for example, this is the simple circuit of series connections. So C1 and C2 are capacitors which are joined to this battery in series, and let us consider that V1 and V2 are the potential difference in C1 and C2 capacitors, and therefore the potential difference can be represented as V is equal to V1 plus V2, where V1 given by this and V2 given by this relation. And if the If C equivalent is the equivalent capacitance of the capacitors combinations, then it can be represented as this. And so if we put equations 5 and 6 in equation 4, then we will get relation 7. Therefore, the net effect of connecting capacitors in series thus decreases the capacitance. So if there are n numbers of capacitors connecting in series, so the equivalent capacitance will be given by this relation. Now, what are the applications of capacitors? So capacitors are basically used in different devices for different purposes. For example, capacitors are used to establish desired electric field. Capacitors can be used for storing energy, as we discussed in our previous slides, and it can confine strong electric fields to small volume. Capacitors are useful to reduce voltage fluctuations in electronic power supplies, to transmit signals, to detect electromagnetic oscillations at radio frequencies, and to other important electronic circuits. So most of the circuits, electronic circuits, capacitors are basically used as a dummy battery which can store charges for future uses. So this is the end of our part 2 of electricity and magnetism. And so let's discuss the electromagnetic induction and other things in the third part of electricity and magnetism.